So we looked at this profile and made a few points, and we wanted to see where the ozone is maximum, and this is the temperature profile that we saw here. This is the real world. How does it compare to the radiative equilibrium calculations we've been making before? Obviously you have to add water vapor as well, as we saw, and this is the water vapor profile. High near the surface and decreases as you go up into the upper atmosphere where it's cold. We will see the details as we go along. Where there is convection, obviously you are taking moisture up, you are condensing and releasing the condensation energy, latent heat, and that's going to drive further motion up and so on till you hit the ceiling and saturation happens, rainfall happens, etc. Right? All those processes we will see. So the radiative equilibrium profile of the atmosphere we had seen in the last chapter. We said there is a jump at the surface when we just do one-dimensional balance of incoming short wave and outgoing long wave. We got fancier and added many layers to make the mass weighted temperature at the top of the atmosphere and the profile more realistic. Nonetheless, it left us with this jump because we didn't have convection, right? So let's look at the same thing again together. So here was the jump in the radiative equilibrium temperature, and it had this profile. We didn't necessarily derive this, but we derived the top of the atmosphere emission temperature average of 255 Kelvin, right? Whereas the typical observed temperature profile looks like this. So you have the realistic temperature that we drove to instead of the top of the atmosphere. You have average of 15 degrees centigrade global mean. So you have a typical profile that looks like this up to the tropopause, right? So the question then is, if anywhere you look at any time, this is the average profile you get, then what is the balance that's happening to maintain this profile? There are some very fast time scale motions in the convection. There are vertical motions that are very fast, relatively speaking, and there are subsidences where the air is going to come down, compress, and get warmer. You're going to get clear skies, dry air, no rainfall, and so on. So how come there are different weather regimes, different seasons, different climate regimes, and you're still going to end up with an average profile that looks like this all the time, right? Except if you go in the middle of the convection and so on. So we will see that there is something very special. We can make a in the first chapter we saw that the sphere that the Earth is got a radius of 6370 kilometers, but the atmosphere and the ocean are thin shells on top of that. Remember, the ocean is only a few kilometers deep, and the atmosphere has no exact definable top, but most of the things are happening within the troposphere, which is 10 to 12 kilometers depending on where you are. At higher latitudes, we will see that it drops off down to about 8 kilometers. So I had briefly mentioned during that time that because the horizontal scales are so large for the atmospheric and ocean circulations, atmosphere is global and ocean is bounded by continents except in the Southern Ocean. So these vertical scales are tiny compared to the horizontal scales. So this allows us to make an assumption that the vertical motions are negligible compared to the horizontal motions. Okay, so assuming the vertical motions are negligible and that the air column is in stationary, not moving, we can derive some balance called hydrostatic balance, which tells us lots of things, and it turns out that this balance can be used over most of the ocean and most of the atmosphere. That's what we will see in the next podcast. Okay, I took time to explain that because it turns out to be one of the most important simple ideas that we must carry in our head. Okay, it also leads us to other cute ideas that we can just know the surface pressure and estimate the weight of the atmosphere. Okay, did you think you could weigh the atmosphere? Well, this relation allows us to do that. We'll see that in the next podcast.